The older I get, the more it seems like the science fiction of my childhood is the research of today and probably the technology of tomorrow. Am I ready? Hello and welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam. I've been living with MS for almost 40 years. You know, I've been keeping you up to date on the research into remyelination, at least to the extent that I know about it. And I've been rather astonished, I imagine you are too, with the amount and the variety of the approaches going on. People are looking at all manner of things. And even so, I found one that seems startlingly new. In fact, it outstrips my ability to even imagine how it's going to work. Why don't we take a look at the article I found? I saw this article on November 6th of 2024, the very day it came out, and it's called Scientists Create Platform for Devices That Wrap Around Nerve Fibers. Polymer sheets controlled with light may offer way of aiding myelin sheath. Now you got to admit, this is a new approach. I have never heard of anything like this before, but I'm fascinated to know more, so let's read on. The article says a new technology is designed to be a wearable device for neurons wrapping around individual nerve fibers with the goal of achieving new ways to study and treat neurological diseases like MS. Still in early testing stages and needing further refinement, the technology was developed by scientists at Massachusetts Institute of Technology. Well, they're pretty reputable, I would have to say. So right off the bat, I'm feeling a little bit more confident that this is a real thing. The concept and platform technology we introduce here is like a founding stone that brings about immense possibilities for future research. Debelina Sarkar, PhD, an assistant professor at MIT and the study's lead investigator, said in a university news story. The technology is described in the paper Light-Induced Rolling of Azobenzene Polymer Thin Films for Wrapping Subcellular Neuronal Structures, published in Communications Chemistry. And they say there's a possibility of moving wearable devices to the subcellular level, which, I find that fascinating. I can't even mentally picture how that's going to happen. Nerve cells use wire-like projections called axons and dendrites to connect with each other and send electrical signals throughout the body, ultimately controlling everything from movement to cognition and emotions. MS is characterized by damage to the myelin sheath that wraps around those fibers. Myelin is essential for the rapid and efficient transmission of nerve signals, so its deterioration disrupts nerve cell communication and causes a wide range of neurological disease symptoms. It's also the first part of the damage that MS causes to our nervous system. So the first thing that happens is the myelin sheath is compromised, with the resulting symptoms that we experience because nerve messages don't get around like they used to. But if it goes on for too long, of course, the nerve itself becomes damaged, eventually destroyed entirely. So that's not what this is talking about. This is talking about the early stages where the sheath is beginning to be compromised, but the nerve is still there and still functioning. And continuing on, the article says, over the last decade or two, wearable technologies have advanced by leaps and bounds. Sensors worn on the wrist like a watch can be used to track everything from how much a person walks to how fast their hearts beat and how well they sleep. In theory, it might be possible to take the idea of wearable sensors down to the subcellular scale. The basic idea would be to create sensors that can wrap around individual nerve fibers, detecting electrical signals or even modulating nerve activity. A main obstacle toward developing this type of technology is that nerve fibers are tiny, twisty, curvy structures. Until now, there hasn't been a way to create technology that can wrap around the fibers tightly enough to be useful as sensors, but not so tightly as to cause harm. Due to their high curvature, axons and dendrites are among the most difficult neuronal structures to conformally enwrap with a synthetic platform, the scientists wrote. They go on to say, though, the technology said to finally control how polymers wrap around the nerve fibers. MIT researchers report having taken a major step in this direction. The team devised a system of using sheets of repetitive molecules called polymers that can be controlled with light. Basically, the flat polymers are injected next to nerve fibers, then light is used to cause the polymers to roll and curl so that they wrap snugly around the fibers. It is possible to very finely control the diameter of the rolling. You can stop it when you reach a particular dimension you want by tuning the light energy accordingly, Sarkar said. So far, the researchers have tested this platform using cell models in a dish in lab settings. Still, they expect that the technology could be expanded to allow for use in living organisms, pending further tests of efficacy and safety. So we are not even at the clinical trial stage yet. And as you know, the first phase of a clinical trial usually recruits healthy volunteers just to see if the thing is safe. Because above all, you want these things to be safe. And now you're injecting some foreign substance into the body, so you can easily see where there might be some problems. So they will be testing this, but so far they seem very optimistic about it. As they go on to say, this work is an exciting step toward new symbiotic neural interfaces acting at the level of the individual axons, said Flavia Vitale, PhD, a professor at the University of Pennsylvania, who was not directly involved in the study. Vitale added that this technology could become a versatile platform to sense and deliver different types of signals, in other words, electrical, optical, thermal, and so on, to neurons and other types of cells in a minimally or non-invasive manner. Future work, the scientists noted, should include integrating and testing materials relevant to work in neurological diseases and evaluating the technology in living organisms. Not only could these interfaces provide modulation, sensing, and drug delivery, but they could also be engineered to electrically and periodically insulate the axons to obtain a synthetic myelin-like layer to study the neurodegeneration dynamics and potential neuroprotection in demyelinating diseases, the team concluded. Wow, pretty fascinating. And like I said, different from anything that we've talked about up to now. Well, of course, I wanted to go out and find out more about this because it is so different. And I just felt like there were a lot of things that the article really didn't answer. I wanted to search on the lead investigator to see what I could find out about her. Turns out she's the lead of a neurologically focused computer laboratory at Massachusetts Institute of Technology, and that this article that we just read together does not really get into this, but it's actually part of an entire strategy of research that her group is doing focused on computing and artificial intelligence and its application to the neurological sciences. And I did find a very interesting video. I'm going to play you a part of it. It'll give you some idea of how her interest migrated from strict computer science models of artificial intelligence to understanding that the brain is similar to a computer. And in her mind, she thinks of the brain as the ultimate computer. And I have to say that that's something that I only partly agree with. The brain is certainly like a computer in some ways, but computers aren't like brains. And so there isn't really an equivalency there in my view. I'd be interested to know what you think. Yes, the brain does all kinds of calculations and associations and all that, but it also has functions that I don't know if AI will ever have. It is the part of us that communicates with God, for one thing. And it also has capabilities of noticing and appreciating beauty. And I don't know if computers are ever really going to be able to do that. I don't know if I want to live in a world where computers are able to do all that. But be that as it may, I want to play this for you so you can just see this piece of research that they're working on in its larger context.
So during my PhD, while I was developing these new kinds of devices for electronic computations, I also got interested in other non-electronic computational systems. And of course, the most amazing one is the biological computer that sits above our shoulders, and that's our brain. The human brain, which is this amazingly complex organ and the boss of our body, it weighs just 3 pounds, but it's the brain that makes us what we are today. And if we peep inside the brain, we will see that it's formed of hundreds of billions of computational elements called neurons. And these neurons, they communicate with each other using electrical and chemical signals. So the brain, it does all its functions but consumes only 20 watts of power, similar to a mere light bulb. But if we were to design a hypothetical supercomputer to simulate the brain, it will consume 10 gigawatts of power, enough to light up 500 millions of those light bulbs. So the brain can be thought of as an ultimate example of low-power computational system. However, at present, we understand very little as to how the brain computes or how the brain works. If we could understand the brain, that could revolutionize the way electronic computations are done today. But that's not the only reason, not even the main reason I got interested in the brain. 1 billion people around the world, they suffer from different brain diseases, schizophrenia, Parkinson's, Alzheimer's, depression, and there's no effective cure for them. If we could understand the brain, that will help us develop new methods and new cures to combat those brain diseases. So why is it so difficult to understand the brain? The electronic circuits, we develop them ourselves. So we know all the individual components and how those components are connected to each other. But Mother Nature has designed the circuits in the brain, and it's so complicated, so intricate, that we human beings have not been able to decipher them yet. And if we zoom into a small region of the brain, we will see that it's formed of a dense jungle of biomolecules, which will look probably similar to the gum wall in Seattle. So in my present research, I'm developing a super resolution technique that helps us to decipher those dense jungles and look into the molecular building blocks of the brain. So in the images here, you are seeing 2 proteins in red and green. They occur in a region where 2 neurons connect to each other. The region is named synapse. So if you just look at these proteins using a conventional light microscope, you'll see 2 overlapping blobs and not much information is revealed, and that's the left image. But when you use the super resolution technique, the arrangement of the 2 proteins, it unfolds beautifully. We are currently using this technique to understand the components of the brain in more details and how they're connected. But knowing the structure is not good enough. We also need to know how the components function as to how the neurons talk to each other. But there are 100 billion neurons in our brain. To understand how these neurons, they work in an ensemble to give rise to our thoughts, our perceptions, our behavior, we need to record from billions of neurons at the same time, a very formidable task. The techniques for brain recording that are existing now, they can record from only a very small fraction of the neurons. An example of such techniques are the optical sensors or the electrodes. There are also techniques which can record from the whole brain, but they measure only an average effect. An example of such technique is the magnetic resonance imaging. So we do not have any technology right now which can measure from each and every neuron of your brain. An ideal solution would be if we could make a tiny device that can go into each and every neuron of your brain and measure the activity from there. Now the brainy electronics could solve this brain problem, not the conventional electronics, because conventional electronics will be too big and they will not fit inside the neuron. Moreover, they will dissipate so much heat that it will just fry up the brain cells. So if I can cook an egg on my laptop, you can well imagine what those electronics will do to your brain. But the devices that I had been developing are extremely low power. Moreover, they are extremely small, so they can easily fit inside a neuron. In addition, since they are made up of this ultra-thin material, they are flexible and soft, and they form a compatible interface with our soft biological systems. Now you must be wondering how this technology can be used to record the activity of the brain cells. So when a neuron becomes active and wants to talk to other neurons, the voltage inside the neuron increases. And I have shown that my devices are 10,000 times more sensitive to changes in voltage compared to conventional electronics. So this technology I developed initially for solving the power crisis of information technology, but I aim to unleash its great potential to solving a major challenge in understanding the brain function. Now suppose we get to a point that we can measure the activity of each and every neuron from our brain. The implications are huge. With that knowledge, it will be possible to replace damaged or dysfunctional parts of the brain with artificial implants. Suppose the connecting link between two neurons is broken. It will be possible to bridge that gap using an electronic chip designed to mimic the functionality of that connection. Again, these devices have to be extremely small and low power. And with such devices going beyond just repairing broken brains, it will be possible to even augment our brain and enhance its capabilities. So the electronic devices, they work much faster than the brain cells because electrons are super light and they can run very fast. But the computations in the brain, they involve movement of heavy ions or structural changes of proteins, which takes time. So if we could replace parts of our brain with electronic counterparts, it will be possible that maybe you will be able to think faster. Maybe we'll be able to make ourselves more intelligent, enhance our memory, and expand the world of our imagination. So all these things will not happen very fast and it will take time. But I believe that it is possible. And how soon that happens depends on how curious we are, how passionate we are in making new discoveries. Because we can solve the brain and transcend it beyond its biological limitations and then go on to solve the other mysteries in the universe. Thank you very much.
So I hope that helps you a little bit to see where they're going with this and give you a chance to think about whether this is something that you could get excited about. If they did a clinical trial, would this be interesting to you? I'm not sure I would want to because, and at least not until they answer some questions that I have. One of them being, is it reversible? You know, if you go to all this trouble of wrapping every single neuron that you have in your brain with this sheath, I can't even imagine that, first of all, but if you could do that, for whatever reason, if you needed to reverse it or wanted to reverse it, could you? Which also says, okay, how would they design a clinical trial that a person could say, well, that didn't work so great, let's take it out again? Is that going to be hard? I don't even know. But see, I'm kind of limited in my imagination when it comes to this sort of thing, so you can maybe picture it. I kind of can't. So that's one thing that I'm very curious about. Another thing that concerns me about this technology is that it's essentially like having a computer in your brain. And if there's a computer, there's got to be somebody that's controlling it, right? There's got to be somebody that's monitoring it, that's repairing it if it breaks, that's giving it instructions, listening to what it says. And you know what? The strong probability exists that that person is not going to be me. So I'm really not sure I want to turn over control of my brain to somebody else, no matter how much I like and trust them. I'm just really also not so sure about this idea of putting so much foreign material in the body, especially in the brain, because the immune system is designed to go after foreign entities. And with multiple sclerosis, we've talked about before how our immune system, our microglia in particular, can get off track and start thinking that things that aren't even enemies are enemies. So how are they going to react to having a whole bunch of these sheaths put in around every single neuron? I don't know. I mean, there's a lot of testing that's going to happen before they're even close to ready for clinical trials, because the safety piece of this, I think, is going to be monumental. I don't even know if you can, within the context of a clinical trial, decide whether this has long-term safety implications. I'm just not sure. We're on the frontier of doing some things that were never possible before. And while oftentimes that's a good thing, we always have to think to ourselves, just because we can do something, does that mean we should do something? Especially since I've seen in some of her other videos, she's looking ultimately at increasing the capabilities of the normal brain, the non-MS brain, just a regular person's brain. I guess what she means is making us smarter, making us able to think faster. I don't even know what all else she's thinking. But that's kind of the ultimate goal, is using AI to turn us into little cyber critters of some kind. I don't know. I don't want to sound like I'm being a Luddite here, someone who doesn't ever want to see progress. I love science, as you can probably tell, and I love the progress we make in areas, but I am cautious by nature, and this looks to me like there's a few red flags. I don't know. If you disagree, I would really love to know. But that is all I have for you today. So until my next video, which who knows, it's going to be probably on remyelination again, because that seems to be the big topic. I just want you to take really good care of yourself, and I'll see you again soon.